Okay, yeah, welcome back. So the plan is that I'll finish up the proof for the lower bound on the extension complexity of the correlation polytope, and then Hamza is going to take over and talk about the SDP extension complexity. Okay, so just a very brief reminder. The correlation polytope, it's the convex hull of these 2 to the n many vectors that are just the outer products of some 0, 1 vectors with itself. It's going to be, it's an NPR polytope. But kind of surprisingly, we can show that the extension complexity is large. And so we do know all the vertices of it, but we don't know all the inequalities. But we can kind of get around that by just taking a family of valid inequalities. And the families of valid inequalities, they go as follows. For every 0, 1 vector A, we can write down, like this inequality, and this is a valid one, which we saw 30 minutes ago. OK, so good. OK, so what it actually means is that we will not show a lower bound on the non-negative rank of the actual slack matrix. We only show a lower bound on the non-negative rank of a submatrix of the slack matrix. That still is going to be a lower bound, because like the non-negative rank doesn't get smaller if you like remove a couple of rows. But the matrix that we're talking about, it has a very nice combinatorial definition. You have the following. It's for every 0, 1 vector A, and we have a row, and for every 0, 1 vector B, we have a column, and the entry is precisely, and this is precisely the slack that we actually calculated in the last on the last slide. So this is just 1 minus the intersection of both like sets or 0, 1 vectors squared. Okay. So it's a little bit like this is the picture. This is like the actual polytope. And now we have, in some high-dimensional weird space, we have some valid inequalities. OK. And in particular, there will be only 2 types of entries that are sufficient for the lower bound. If A and B are disjoint, then if you plug this in here, then we'll see a 1 in the matrix. And if A and B share precisely 1 index, then we will see a 0 in the slack matrix. And the magic is that actually we don't care at all about any other entries. Just this property will be enough to show that the non-negative rank is 2 to the n. OK. By the way, there is a nice geometric interpretation what it means if you have only a subset of valid inequalities and not all of them. This is just a side remark. One can actually show the following. If you have some points x, and they lie in, they all satisfy some valid inequalities, and you define as like a partial slack matrix of these points with respect to these inequalities. So it's a little bit like you have the convex hull of your points, and they are contained in these inequalities. If you look at the partial slack matrix of like these points with respect to these inequalities, then you can also wonder what is actually the non-negative rank. What is the meaning of the non-negative rank of this matrix? It has precisely the following meaning. It is the extension complexity of the smallest polytope. It is the smallest extension complexity of a polytope that you can sandwich between x and p. OK, so we don't actually need that, but it's a nice geometric insight. And this can be proven very similar to Yanakaki's theorem. OK, but anyway, we have our partial slack matrix, and we want to show that it has a high non-negative rank. And we will actually use the rectangle covering lower bound for that. OK, so again, there are these 2 families of entries. We have tuples A and B that are disjoint. And for those tuples, we'll see a +1 in the select matrix. And if you do a quick calculation, like how many of these entries do you have, then these must be 3 to the n. OK, just double check that you're not all sleeping. Why 3 to the n? Well, for every index, I, there are kind of like 3 choices if you want disjoint tuples. It's like none of like A1 and BI, AI and BI are 0, or one of them is 1. So there are 3 options. And so you have 3 to the n, many choices. OK, good. So on the other hand, there are these other entries where A and B share precisely 1 symbol. And we calculated that actually then in the select matrix, you will see like the opposite. You will see a 0. OK. So if you now apply the rectangle covering lower bound, then in particular, you know that there must be some number of rectangles, at most extension complexity, many rectangles, and they are covering at least, the ones, these 1 entries here, and they definitely, they cannot contain any of the 0 entries. OK? OK, so we have to show that, there are plenty of those rectangles needed. And the most obvious way is just to have a counting argument. And so the most obvious thing would be to show that actually whatever rectangle you have, well, it's not allowed to contain any 0 entry, because then it couldn't be part of a rectangle covering. And then just bound like how many of those 1 entries here can you have. And in fact, one can show that this is at most 2 to the n. OK, now how many rectangles do you need to cover 3 to the n many entries if every of your rectangles can cover at most 2 to the n? OK, you can do the math. So that's exponentially many. OK. Now, so this is the only thing that remains to be proven, that whatever rectangle you have that does not contain a pair AB sharing 1 entry, you can cover at most 2 to the n of these entries. So, OK, that's the statement. OK, and we'll prove this by induction. OK, so how do you prove things by induction? Well, you have n elements. You take element number 1, and you mess around with it. So we'll do the following. Imagine this is our rectangle. It has many A's and many B's. And let's sort them so that these are the B's that don't contain the first symbol. These are the B's that do contain the first symbol. And these are the ones that, these are the A's that don't contain 1. And these are the A's that do contain 1. OK, so you want to prove things by induction. So we'll define another rectangle, which is like a smaller one. It's a subset of our rectangle where we take only the B's that don't contain 1. OK. Similarly, we define a second rectangle where we take all the pairs AB in our rectangle where the 1 is not contained in A. OK. So the bound you want to prove by induction is 2 to the n. You split your problem into 2 parts. Well, OK. And now you want to do the following. So each of these is a rectangle that does not contain a pair AB sharing precisely 1 symbol. Because OK, sorry, no. OK, now we're doing the following. We delete the symbol 1. OK, we delete the symbol 1 from all the tuples. And then we want to apply induction because now we have 1 symbol left. Okay, so if you stare at, let's say, the blue rectangle here, then you only took the B's where 1 was not contained in B. So if you now, what happens if you delete the symbol 1? Well, the 1 may have been in the A's, but the 1 was never part of an intersection pattern. So deleting it does not change the intersection. So still, we have two rectangles, R1 and R2, that do not contain a pair AB sharing precisely one symbol. OK, that's good. So we have our subproblem. We could split it into two parts. We apply induction, and everything is good. And in particular, we also covered all the entries that are disjoint. Because like this area here doesn't have disjoint pairs at B, because like 1 would be contained in A and in B. Okay, there is an issue here. So you would like to finish the proof here, but that would be a little bit too fast. Okay, where's the issue? The issue is the following. Imagine you have a set A that doesn't contain 1. And this is in the rectangle, and also this thing, union 1, is in your rectangle. And now, if you delete the symbol 1, then kind of you have a tuple that collapses to the same. And now you're counting it, but you're counting it only once, but you should have counted it twice. So your counting is messed up. OK, not good. On the other hand, staring longer at this, this tuple is counted in the blue rectangle. This one, it's also counted in the red one. It's counted in, well, it's contained in both rectangles, and then you're deleting things and things collapse. But it appears twice and it is counted twice because you have two rectangles. So that's good. 2 and 2, fine. But there could be a problem. There could be a problem that actually there is a pair AB, none of them containing 1. They are in R. Also, the pair B and A union 1 is in your rectangle. And also A and B union 1 is in your rectangle. Then these collapse. The tuples collapse. You're counting them twice, but they exist 3 times. So then you haven't counted them enough. But this is not happening. So why is this not happening? Because, well, then you would have this thing in your rectangle, you would have this thing in your rectangle, and they would intersect precisely in that symbol 1, and this would be a forbidden pair. But you don't have forbidden pairs. So we're good. OK? It's a beautiful proof by Keibel and Weltke. It was not the one that was originally used, but it's one that I actually like quite a bit. OK, questions? So this was actually the complete proof that the correlation polytope has an extension complexity of at least 1.5 to the n. And OK, so that's the end of this part. And now Hamza is going to take over, and he's going to explain how SCP extension complexity work.
Other questions for Thomas? Okay, if there are no questions for Thomas, I'll start. Okay, so I'll talk about semi-definite programming lifts. Okay, so I guess Michel and Pablo already talked a lot about semi-definite programming and so on. So I will not have to do a lot of introductions. So essentially, what is a semi-definite programming? So this is the picture that Pablo drew on the board. So a semi-definite program is essentially the problem of optimizing a linear function over a set that has the following geometric picture. So it's the intersection of the positive semi-definite cone. So it's the cone of d by d symmetric positive semi-definite matrices with an affine subspace that I call L here. Okay. And so I'm going to say that a convex set C has a semi-definite programming extended formulation or a semi-definite programming lift if it can be written as the projection. So pi here is a linear map of such a set, okay, of the intersection of an affine subspace with the cone of positive semi-definite matrices. Okay. So the reason we're interested in such a representation is because if you have such a representation of your convex set C, then essentially optimizing a linear function over C becomes a semi-definite program, okay, of size d by d. Okay, and so the SDP extension complexity of a convex set C is the smallest size of an SDP lift, where I measure the size of the SDP lift as the size of the cone, so the D here. Okay, this is somehow of a proxy to the complexity of solving the SDP of size D. So note, for example, so this is a generalization of linear programming lift. So if your subspace L here is included in the subspace of diagonal matrices, then what you get upstairs is a polytope. Okay, and so what you essentially get is an LP lift of, so here it has to be a polyhedron. Okay, so the LP extension complexity that Thomas talked about is always greater than or equal than the SDP extension complexity. Okay, so is the definition clear? Yes. Okay, so let's look at a very simple example of an SDP lift of a convex set. Okay, so here I'm going to take my convex set is going to be the square, so that's minus 1 square. That's what is represented here, and I'm expressing here my square as a linear projection of a certain spectrahedron. So that's an intersection of an affine subspace with the cone of positive semi-definite matrices. So this spectrahedron is described by this thing. Okay, so you look at 3 by 3 positive semi-definite matrices with a diagonal equal to 1. Okay, so that's a 3-dimensional convex set. And the claim is that if I project this convex set on these components x and y, what I get is the square. Okay, so that's an SDP lift of the square of size 3. So why is this equality true? Okay, why is this true? Is because, let me just give you maybe one direction is, if this matrix is positive semi-definite, then you see that all the 2 by 2 minors have to be non-negative. Okay, so this determinant has to be non-negative, so 1 minus x squared has to be non-negative. The same 1 minus y squared has to be non-negative, and so x has to be between minus 1 and 1. And the other direction, I'm proving that this is included in this is also not difficult. So this is one example. So you see that the convex set here in this case was a polytope, but of course you can do things other than polytope. So the other example that this was actually in Pablo's talk, if you look at the nuclear norm ball, so that's the set of matrices of size n by m whose the sum of singular values is less than 1. That's called the nuclear norm ball. That shows up in many applications. Has a semi-definite representation. Okay, which again is the one that Pablo mentioned. Okay, so here the additional variables are x and y. Okay, and the size of the representation is essentially m plus n. Okay, because this is the size of my matrix here, of my PSD. Okay, and another example. So I haven't written it up explicitly, but that was mentioned in Michel's talk is that the stability number, the stable set polytope of a perfect graph has a semi-definite extended formulation that was shown by Lovash. Okay, and the size of this formulation is n plus 1, where n is the number of vertices. Okay, so these are just some examples. So there's one kind of key difference between LP extended formulations and SDP extended formulation is that you can actually do convex sets. Okay, so in the LP world, if you take a polytope and you project it, you get another polytope. Okay, but here you can potentially get convex sets that are not polytopes. Okay, and so we saw the nuclear norm ball. Okay, so of course, yes.
Is it trivial to? Is there a trivial upper bound on the complexity, extension complexity of convex set?
So a trivial for any convex set, you mean, or? Yeah. No. So I'll come to this right now. Actually, okay. So. Yeah. Not all convex sets have a semi-definite representation, but that's actually a very recent result. Okay, it's not. Yeah. So the question that you can ask is what are the convex sets that actually admit in the first place a semi-definite representation? Okay. So there's one necessary condition that you can write. Okay. So of course C has to be convex. Okay. This is clear because the linear map of the linear image of a convex set is convex, but you can also see that it has to be semi-algebraic. Okay, so remember, what is a semi-algebraic set? A semi-algebraic set is a set that can be defined using polynomial equations and inequalities. Okay, so an example of a non-semi-algebraic set is the epigraph, say, of the exponential function. Okay, you cannot write it using polynomial equations and inequalities. You can approximate it as closely as you want, but you cannot write it exactly. Okay, the reason a semi-definite representable set has to be semi-algebraic is the following, is because, I mean, the cone of positive semi-definite matrices is defined using polynomial inequalities. Okay, that's the minors have to be non-negative, and then you intersect it, you get a semi-algebraic set, and then there is the result of Tarski and Seidenberg that tells you that when you project a semi-algebraic set, it has to be semi-algebraic. Okay, so that's the first necessary condition that you can write. It has to be convex and semi-algebraic. Okay, and then there is of course the question that is it true that any convex semi-algebraic set is semi-definitely representable? Okay, so this question has kind of some history in optimization, in continuous optimization. So let me just mention briefly. So anyone in continuous optimization knows about this book. Okay, so this book is by Bental and Nemirovsky. Okay, so two famous continuous optimizers. So this book is essentially a compilation of a lot of convex sets and their semi-definite representations. Okay, so it gives you, for example, it tells you how to give semi-definite representations of the LP norm ball for any p bigger than 1 that is rational, for the Schatten LP norms, the nuclear norm ball, sums of k largest eigenvalues, geometric mean of eigenvalues. I mean, many convex functions that shows up in practice, they give semi-definite representations for them. And in fact, all of these are implemented in software that people in continuous optimization use. Okay, so like this is really the underlying results that underlie really CVX and YALM, if you know what these software are. Okay, so these are tools that allow you to easily solve optimization problems. So this is this is the book by Bental and Nemirovsky, and then so Nemirovsky was invited as a plenary speaker at the ICM in 2006. And then he posed this question: is it true that any convex semi-algebraic set has a semi-definite lift? Okay, and he said that this question seems completely open. Okay, if you read his kind of his survey. So then there were some results by Bill Helton and Jiawang Nie in 2009 and 2010 that showed essentially that if the boundary of the convex set C is smooth and has positive curvature, then it has an SDP lift. Okay, so they showed a series of results that essentially the results have the following flavor: that is, if the boundary of the convex set C that is semi-algebraic is smooth and has positive curvature, then it has an SDP lift. So let me just kind of pause a bit and talk a bit about this assumption. So this assumption looks innocuous, but actually it's quite a strong assumption. Okay, so many of the convex sets that we deal with in practice are actually non-smooth. I mean, their boundaries are non-smooth. If you just think about the positive semi-definite cone, the boundary of the positive semi-definite cone is non-smooth. Okay, so it is essentially the boundary of the positive semi-definite cone can be stratified according to rank. Okay, each stratum is smooth, but the boundary as a whole is not smooth. Okay, and in fact, if you just think about polyhedra and so on, these all have boundaries that are non-smooth. So this is quite a strong assumption. Okay, so this is. So nevertheless, I mean, they actually conjectured at the end of the paper that this is true, that any convex semi-algebraic set has a semi-definite representation. And then, algebraic geometers then jumped into this problem. So in particular, Klaus Scheiderer, who is at the University of Konstanz, he showed actually that the conjecture that they proposed is true in the plane. Okay, so they showed that any convex semi-algebraic set in the plane, so in dimension 2, has a semi-definite programming lift. In fact, he actually showed more generally, he showed that in any dimension, the convex hull of any one-dimensional semi-algebraic set has a semi-definite programming lift. So I mean, if you take a convex semi-algebraic set in the plane, its boundary is a one-dimensional semi-algebraic set. Okay, and so this is why it implies in particular the conjecture in the plane. So there is one case where you can actually prove this relatively easily. Is if you look at the convex hull of what we call rational curves. Okay, so these are curves that have a rational parametrization, and this was actually a result of Pablo that he showed, is that these do have an SDP representation. Okay, so Klaus essentially generalized this to the convex hull of any algebraic curve in the plane. And then very recently, this is just last year, Klaus showed that there are actually many convex semi-algebraic sets that do not have an SDP representation. Okay. So let me actually let me mention. So he showed that there are many of these, and I mean his construction is actually really explicit. So he shows that the cone of non-negative polynomials, whenever these are different than sums of squares, do not have an SDP representation. So remember that. So I can define the following cone. So Pn2D. Okay, so this is the set of polynomials in n variables of degree less than 2D. Okay, such that P of x is non-negative for any x in Rn. Okay, so this is a convex cone. So remember the picture that Pablo did on Monday, I guess, is so you can look at the following table. So you look at the number of variables. Okay, so 1, 2, 3, 4, etc., and then the degree. And you can ask, when is it true that any non-negative polynomial in n variables of degree at most 2D is a sum of squares? Okay, and so he showed that this is the case in this situation, and this was somehow the exceptional case that Hilbert showed, and then these are all the situations where this is not true. Okay, so in all these cases, we know that this cone has a semi-definite representation because we know that sum of squares, polynomials that are sum of squares, can be represented using SDPs. So what Klaus actually showed is that in all these other cases, there is no hope of finding any semi-definite representation. Okay, so no matter how clever you are and so on, you cannot find one. Okay. So this is it. So yeah, so this is all I wanted to say about this. The proof is relatively technical and so on. It uses a very heavy algebraic geometry. Maybe Cynthia, you can ask Cynthia about it. Yes. So this was kind of about the story of which convex sets admit a semi-definite representation. So from now on, I'm going to actually talk about. I call this the existential question. Okay, this is more of a mathematical question. Now, what I'm going to talk about, in the rest of the talk, is more the complexity question. Okay, where essentially you take a convex set that you know has a semi-definite representation, which is typically a polytope, and you ask what is the smallest possible semi-definite representation of this. So it's 3:30. I have until what time? Until 4?
1 hour. Until 4. 4 o'clock.
Until 4. Okay, so I have half an hour. Okay. So let's work with polytopes. Okay, so I have a polytope P. So Thomas talked about slack matrices and how slack matrices allow us to understand the LP lifts of polytopes. I'm going to do exactly the same, and I'm just going to introduce a new notion of factorizations of matrices, and I'm going to show that this is related to SDP lift of the polytope. Okay, so remember that the slack matrix of a polytope is defined as follows. So it's a matrix where the number of rows is the number of facets of the polytope, and the number of columns is the number of vertices of the polytope. And the ijth entry is essentially the slack of the jth vertex with respect to the ith facet. Okay, so this is bi minus ai transpose vj. Okay, so that's a non-negative matrix. So let's just to give a very concrete example. So if I look at the square again, and this square has 4 facets and 4 vertices, how do I construct the slack matrix? So I look at the first facet, and I evaluate it at the 4 vertices. So say I ordered the vertices in this way, so this, and this. So I'm just going to copy these numbers, 0, 1, 1, 0. And then I look at the other facet, I get 0, 0, 1, 1, etc. So these are just the cyclic permutations of these. Okay, so this is the slack matrix of the square. So now I'm going to introduce a new a notion of factorization of non-negative matrices. Okay, so that's called the positive semi-definite factorization. So if I take M, a matrix with non-negative entries, I can try to factorize my matrix as follows. I want to find PSD matrices AI and Bj of size d by d, such that the ijth entry of my matrix is equal to the trace of AI and Bj, okay, or the inner product of AI and Bj. Okay, that's the trace inner product. Okay, so the trace inner product of two positive semi-definite matrices is always non-negative. Okay, and so that's why M has to be non-negative. Okay, so the smallest d is called the PSD rank of my matrix. So you can see that actually the PSD rank is always smaller than the non-negative rank. Okay, so why is this the case? Yeah, okay, so just take diagonal matrices AI and Bj. Okay, but it can actually be substantially smaller. So let me give you a simple example. Let's look at this matrix M. So it's not a slack matrix, it's just kind of to play around a bit with this notion of PSD factorization. This is the matrix I minus j square. Okay, this is the ith and jth entry is I minus j square. So this is how the matrix looks like. So you can show that the PSD rank of this matrix is equal to 2 independently of n. Okay, of the size of the matrix. So how do you do this? So this is just a factorization given as follows. So I'm going to associate to the ith row the following matrix. So 1i squared. That's actually a rank 1 PSD matrix. And I'm going to associate to the jth column Bj, which is just, again, this rank 1 matrix. And you can verify very easily that Mij is equal to the trace of Ai and Bj. Sorry, that should be an I here. Okay, if you just do the inner product of these two, that's just the inner product of this vector with this vector squared. So that's just minus j plus I the whole squared. Okay. On the other hand, it's not difficult to show that the non-negative rank of this matrix grows with n, and it grows as log n. Okay, you can show it's an easy lower bound that this grows with log n. In fact, it's actually, I think, equal to, it's smaller also than 2 log n or so. So yeah, there can be a big gap somehow between the PSD rank and the non-negative rank. So the theorem now is the theorem I think that you would expect, is that if I take a polytope P with a slack matrix M, then the SDP extension complexity, so remember this is the smallest SDP lift of P, is equal to the positive semi-definite rank of the matrix M, of its slack matrix. Okay, so this is the analog of the theorem that Thomas mentioned. Okay, and in fact the proof is really very similar. Okay, it just uses duality or Farkas lemma for SDPs. So maybe I can actually go over the proof just to. Okay, so again there are two directions in the proof. Right, so I take P, okay, this is the convex hull of a certain set X, okay, so my slack matrix is indexed by the facets and the vertices X of the polytope, okay, so I'm going to assume first that M has an SDP factorization okay, of size D. Okay, so this means that I know that Mij, which is essentially Bi minus Ai transpose Xj, is Ui comma Vj. Okay, and I want to show that my polytope P has an SDP lift of size D. So I'm going to use exactly the same thing that Thomas did. So I'm going to write, so I know that P can also be written in the following form. So this is B minus AX non-negative. Okay, so and then I'm just going to say that this is the set of X in Rn such that B, so I'm going to write it this way, is is equal to ui comma v, where v is positive semi-definite. Okay, so I have to say here there exists. Okay, so I'm essentially going to write this. So I'm going to introduce this additional variable v. Okay, and I claim that this equality is true. So clearly, if I take an x that is here, then I know that b minus ax is non-negative because the inner product of ui and v is non-negative because ui is PSD and v is PSD. So this gives us one inclusion. Okay, and the other inclusion uses the fact that x is the set of vertices of my polytope. Okay, so what do I have to show? I have to show that anything in here is in here. Okay, so if I take a point in here, I know it's a convex combination of elements of x. Okay, and so I know that for each element of x there is a certain vj, and if I just take v to be the convex combination of these things, I'm going to get this this equality. Okay, it's an easy proof. So it's again exactly similar to what Thomas mentioned. And then you can also show the other direction. So the other direction, this is what where you see the Farkas lemma showing up. So what do we want to show? So we want to show that I'm going to assume that P has an SDP lift. Okay, so in particular, I'm going to write this SDP lift in a certain form, and this is without loss of generality. So such that F0 plus okay, so I'm going to assume that the projection is actually just forgets a certain number of components. Okay, so so I have to show that my slack matrix has a positive semi-definite factorization. So how do I do this? So so I look at a certain facet. So that's a certain row of my matrix. So B minus A transpose X. This is non-negative for any X in P. But then I can actually also think of this as a valid inequality on my convex set upstairs. Okay, so I know that this is true also. So I'm going to lift. Essentially, I'm going to think of this as a valid inequality as upstairs. So this is B minus A transpose X is non-negative for any X, Y, okay, in my spectrahedron S. Okay, so this is my spectrahedron S is essentially the set of X, Y that satisfy this. Okay, so let me write. This is the set of X, Y. But then now what does Farkas lemma tells me? Farkas lemma tells me that since I have here a valid inequality that is true on this, then that this inequality has to be essentially something that you can obtain by taking non-negative combinations of this. Okay, but in the SDP world, what this means is that you essentially hit this with another PSD matrix. Okay, so let me make this a bit more clear. So if you look at the set of X, Y that satisfy this PSD constraint, then you can think of what are the valid inequalities that you can generate from this. Okay, and so the valid inequalities, one way to generate such inequalities is to just pick any PSD matrix, call it B, say, and hit it, and hit this matrix with it. Okay, so you look at B comma this, and this will always be something that is non-negative on the spectrahedron. And what Farkas lemma tells you is that this is everything that you can get. Okay, that any valid inequality on this has to be of this form. So then this implies, this is Farkas lemma, that B minus A transpose X has to be of the form, say U, comma, F0 plus X1, F1, etc. plus Y1, J1, M. And this is true for any xy. Okay, so this is an equality of linear forms, really, of affine forms. So for any xy in Rn cross Rm. Okay, and then now we're actually almost done, because now what I only have to do is to get my factorization. So remember, I want, so I have my u, this will be the thing that indexes my row, which my row is indexed by a facet. And then now I pick a vertex, and I know that the vertex actually has to have a certain y above it that lives in the spectrahedron. Okay, and I'm just going to take my PSD factorization to be this matrix for the corresponding y. Okay, so for any x in X, I know that there exists a certain y of X such that xy of X lives in S. Okay, and I can just so I'm just going to take V of X to be this whole thing. Okay, so let me just write F0 plus, I'm just going to write this, so. Okay, so where f of x here is just this linear form and g of y is this linear form. Okay, so this is PSD. And what I get is essentially that B minus A transpose X is U comma V of X. Okay, so where U and V of X are PSD. Okay, so, and this is, so this is my factorization of, I don't know if it's visible, but so this is my factorization of the slack matrix. U here depends only on the facet, which corresponds to B and A, and V only depends on X, my vertex. Okay. Okay, so the proof is really simple if you didn't kind of follow maybe all the details. It's just really an application of Farkas lemma. You take a linear inequality, you lift it upstairs, and then. So yes, so maybe what I want to explain is actually the connection with sums of squares. Okay, so Pablo and Ankur talked a lot about sums of squares and so on, and I want to explain what is the connection between lifts of polytopes and sum of squares hierarchies and sum of squares certificates and so on and so forth. Okay, so what I'm actually going to start from this. So I know that, so what we've essentially showed is that if you have an SDP lift of a polytopy, then what you have is essentially a certificate of non-negativity of all your facets of the following form. Okay, so you have B minus A transpose X, okay, is equal to U comma V of X for any X in X. Okay, so X are the vertices of my polytope, but and U and V are PSD. Okay. So if I decompose U and V, so since they're PSD, I can write them in the following form. So U is just the sum of UI transpose. Okay, and V of X I can write as the sum also of VI of X and VI of X transpose. Then what I actually get is that B minus A transpose X is the sum of UI transpose Vj of X squared. Okay. I'm just going to expand this. And so what have I actually just done is that I've written my facet inequality again as a sum of squares of certain functions. Okay, so I'm going to write this as just H alpha of X squared. Okay, where my H alphas, what they are is that they're linear combination of certain functions Vj, okay, defined on X. Okay, so here my H alphas belong to a certain subspace V, and my subspace V is just the span of the functions. So Vj is a vector, so these are Vjk, J from 1 to D, and K from 1 to D. Okay, So again, what is inside here is the sum. This is an inner product, and Vj is a vector. So what we've written is that we've expressed this facet of the polytope as a sum of squares of functions from a certain subspace V, and the dimension of this subspace is smaller than d squared. Okay, and remember, d squared was the size of the lift that we started. So let me just then summarize in the theorem. Right. So what we've just shown essentially here is that if I have an SDP lift of size d, okay, so x here are the vertices of my polytope, then there is a subspace V of R to dx. So R to dx here represents the set of functions on x, such that the following holds, that the dimension of V is smaller than d squared, and such that any facet of P, or actually any valid inequality on P, has a sum of squares certificate where the functions h alpha here are from the subspace V. Okay. And in fact, this is an if and only if. Okay, it's also not difficult to show that if such a subspace V exists, such that any facet of P has a sum of squares representation from V, then the polytope has an SDP lift of size the dimension of V. Okay, so there is a gap here. This is d squared, this is d, but it's not too important. I mean, it's you can bridge it if instead of looking at scalar sums of squares, you look at vector sums of squares. But it's not the main point. Okay, and so are there any questions about this? Is this kind of clear? What this? I mean, I just want to make the point that constructing an SDP lift of a polytope, okay, is equivalent to certifying the facet inequalities of this polytope using sums of squares from a certain subspace, and the dimension of this subspace is what governs the size of the SDP lift. Okay, so if you're familiar with the Lasserre hierarchy or the sum of squares hierarchy for describing convex hull's of points, then the Lasserre hierarchy actually corresponds to the choice of V being the subspace of polynomials of degree at most k. Okay, so if you think of you can think of polynomials of degree at most 1, 2, 3, 4, etc. on x. Okay, and you can try to certify the facet inequalities of P as sums of squares of degree 1, 2, 3, or 4, etc. Okay, so this is exactly what the Lasserre hierarchy does, is that it tries to do this, it tries to certify this, and the Lasserre rank somehow of the polytope is the smallest k, such that you can certify all the facet inequalities using polynomials of degree at most k. Okay, are there any questions about this? I'm going to give some examples now. Okay, so let's look at an example just to make things a bit more concrete. Let's go back to our square, okay, and let's look at what this picture does it tell us. So the square is just the set x here. In this case, is just -1, 1 squared. It's a set with 4 points, and I have 4 facet inequalities. So 1 minus x1 non-negative, 1 plus x1 non-negative, and so on. Okay, and what I'm going to try to do is to try to write these facets as sums of squares from a certain subspace. Okay, so what you can easily show, if you try to look at this function 1 minus x1, you can actually find this sum of squares or this square just certificate. So you can show that 1 minus x1 is 1/2 of 1 minus x1 squared on the hypercube. Okay, it's very simple. You just develop this. So you expand. So you get 1 minus 2x1 plus x1 squared, and you get your thing. So this is a sum of squares certificate of the non-negativity of this on here. Okay, so now we have to look at what is the subspace of functions under the square, okay, that we used in this sum of squares certificate. So this is just the polynomials of degree at most 1. So here V is the span of constant functions x1 and x2. This is a subspace of dimension 3, and this gives us a lift of size 3 of the square. Okay, and this lift is actually nothing but the lift that I showed at the very beginning, okay, with the ones on the diagonal. Okay, so here I only showed one facet, But you can also, it's very easy to see that all these do have sum of square certificates from this subspace V. Okay, so really the key idea is it's simple. So you have a certain convex set or a certain polytope. There are certain non-negative functions that you associate to it. These are just the valid inequalities. And finding small certificates for these valid inequalities allows you to get a small lift of this polytope. So now I want to show a slightly more complicated example. So to kind of look at the difference between the subspace. So here this is the subspace of polynomials, of linear polynomials of degree at least 1. And I want to try to see if you can try to look at subspaces that are different than the ones that are used in the Lasserre hierarchy. Okay, so this is the example of regular polygons. So this is maybe slightly more complicated than the square, but not that much complicated. So I'm going to take the example where x are the n roots of unity. Okay, so this is you have the unit circle. You look at the n roots of unity here, the 7, n equals 7. And I want to try to construct an SDP lift of this polytope, okay, in the plane. So again, what I have to do is I have to look at the facets of this polytope and I have to try to certify them using sums of squares. Okay, so the first, if you write the equations of this facet, okay, so this is what you get. This is cosine pi over n, etc. Okay, and it's not very difficult to show that if you want to certify this, that this thing is non-negative for any x, y root and n through root of unity, then you need to use polynomials of degree at least n over 4. Okay, you need to go to quite high degree to be able to write a sum of square certificate of this. Okay. It's not very difficult to show, but essentially the reason is because if you use a smaller degree, the identity that you would write would be valid on the whole square, on the whole circle. Okay, I mean you would not feel the fact that you are on the n roots of unity, and so it would hold on the whole circle, which is not true. So what this means again is that remember how the Lasserre hierarchy work is that you try polynomials of increasing degree is that and until you can certify the non-negativity of this. And so what this tells us is that you have to go to degree at least n over 4. Okay, so here in this case it would be n over 4. So this would actually give you a lift that is quite big. So it would give you a lift that is of size roughly n also, so n over 2. Because in this case, this is a very special case where actually the polynomials, so each subspace here, pol 1, pol 2, etc., are the homogeneous polynomials of degree 1, 2, etc. Each one of these have dimension exactly 2. Okay, these are the harmonic polynomials, and these are essentially the cosine and sine. So this is the cosine 2 theta, sine 2 theta, cosine 3 theta, sine 3 theta, and so on. So the question is, can you actually find a subspace to certify this thing, and the subspace has much smaller dimension than linear in n, okay? And it turns out that you can, okay, that you can find such a subspace, okay? And the idea is actually to pick and choose some of these polynomials, so to look at sparse polynomials, okay? So to do something like this, okay, and to take the subspace to be just to skip many of these monomials that you would not need. And so how do you do this? So you have to find a certain sum of square certificate of L that has this sparsity pattern, and in fact such you can, okay, here is it. So you can show that this is true. So I will not show it, but essentially this is a sum of square certificate of L. Okay, and the key point here is that you see what is under the square is also, this is the constant. This is a monomial of degree 2 to the j. And this is another monomial of degree 2 to the j. Okay? So essentially what this means is that the only thing that you need are the monomials of degree a power of 2. Okay, so you do not need really all the monomials in between 1 and n over 4. You just need the ones that are a power of 2. And so how many such monomials are there? I mean, there are log n such monomials. Okay, so if you go from 1 to n. And so what this actually tells you is that you can find a subspace of much smaller dimension than the one that Lasserre, that is considered in the Lasserre construction. And this subspace has dimension log n. So it gives you a lift of this polytope, an SDP lift of this polytope of size log n. Okay, so I just wanted to kind of, again, mention this example. So maybe the regular polygon is not a very interesting, polytope per se, but just to illustrate this idea of choosing, of this choice of subspace, is that if you want to rule out essentially, so a lot of work has been done into proving lower bounds on the Lasserre hierarchy. So where you want to show that you cannot certify such non-negativity of something using polynomials of degree less than something. To prove lower bounds on SDP lifts, you need to show that you cannot do so with where the subspace has a dimension smaller than something. Okay, so it's a much, it's a much more complicated endeavor somehow. So are there any questions about these examples? No questions? Is it clear? Yes.
I have a question about the more general approach. So, as far as I recall, you mentioned that the sum of square certificates actually provides an upper bound on the upper bound on the semi-definite, the size of the semi-definite extension.
Yes, yeah. It's tight. It's the same thing. Yeah. So yeah, it is tight. Yeah, it is. I mentioned so here, yes. So we show that if you have an SDP lift of size d, then there exists such a subspace of dimension at most d squared. But you can also show conversely that if such a subspace exists, then there is an SDP lift of size the dimension of v. So it is tight, yeah. It is exactly. Any other question? Yes.
So for polygons with LP lifts, what can you do?
Yeah, you can actually do log n with polygons also. Yes. It's a completely different construction. So this one is really an SDP construction. And the other one is due to actually Bentel and Nemirovsky also. So yeah. Yes. Okay. Yes. Let's actually see, what do I have? Yeah. So maybe can I finish with this? And then I have, I think, 2 minutes or so. I'll finish with this. So I wanted to kind of finish all this picture with this table. So I was going to write it on the board, but yeah, that's fine. So essentially the connection between hierarchies and extended formulations, okay, in the LP and SDP case. Somehow to summarize a bit the story. So we saw that constructing an extended formulation amounts to certifying non-negativity of the facets of a polytope. Okay, so we saw that for SDP extended formulations, the way you do this is that you try to write your facets as sums of squares from a well-chosen subspace. Okay? And we saw that for the Lasserre hierarchy, this subspace essentially corresponds to the polynomials of degree at most k. So how does this picture, what is the analog of it in the LP case? So in the LP case, essentially what the picture that Thomas explained can be also transcribed as follows, is that you want to essentially write your facet inequalities as non-negative combination of certain well-chosen AIs. Okay, so these AIs are actually nothing but either the column or the rows of one of the matrices in the LP factorization. Okay, and the other column essentially gives you the non-negative weights that you need to express all the facets. Okay, so if you think of all the facets, each row is essentially a facet evaluated at x. A non-negative factorization tells you that each row is a non-negative combination of the rows of the V, of the second matrix in your thing. And so if you interpret these the rows of the second matrix as the AIs, okay, this is essentially the picture. Okay, so it tells you, and these are the certificates of non-negativity of your L. Okay. And so what do the hierarchies? Again, the hierarchies are a special case of this when the AIs are very special functions that you chose on X. Okay, if you think of, say, the Handelman hierarchy, or the maybe most commonly known as Shirali-Adams hierarchy, which is in the particular case when X is a subset of the hypercube defined using certain polynomials, it's very easy to construct non-negative polynomials on this set. You can, for example, take any power of X. So here x1 to the alpha 1 and so on, and any power of 1 minus x, and then you can also take products of these GIs. This gives you certain non-negative functions, and then you can try to certify your facets as non-negative combinations of these. Okay, so again, the Handelman and Shirley-Adams hierarchy are a special case of extended formulations when these AR take this form. And then again, you form a hierarchy by putting a bound on these alpha, beta, and gamma, and so on. Okay, so I hope kind of this gives you a unifying picture of how things just interact together. And yes, I think I'll close with this. Yeah. Thank you.
Any more questions? If not, we'll take a break.
Thank you.